Okay, this is the continuation of last week. I've changed the title slightly. I think this is a better representation of what we're talking about. It's this exercise in inventing sequence models from the point of view of vector signal processing. So you just think of the vectors as signal samples, and all the processing that happens is a signal processing context. And so with that point of view, a lot of ideas flow forth. And so let's see what we have. So we got about as far. So we got to this point, and then we introduced gating. So I just pick it up here, where this is a one-pole digital filter. You have this input. So this is normally a sequence of samples, such as pressure at each time instant for a microphone input. But in this case now, it's a sequence of vectors. And so the underbar means vector. N is the time step, so it's a vector at time n. And it's a long vector. In the original transformer, it was 512, and nowadays it's thousands. It's a very long vector. And so here's a depiction of the n equals 3 case, just if it's a 3 vector. And the idea is that we're going to throw vectors into this memory as just a sum. So this sum just adds them up. And this is a one sample delay. And so it just says, take the previous sum and then add the new vector coming in. And so this is our vector memory. It's just a single vector, but we can visualize it like this, where it's, and the reason it's a unit sphere is because, as we talked about last time, there are reasons to normalize. And you can see in the modern sequence models that there's RMS norm used quite a bit. So this does get enforced at various points in many networks. And so so it's just a nice nominal place. Oh, and I just saw over the past week that sentence embedding, what is it, the BERT-based sentence embedder has an optional argument for normalizing the norm to 1, which allows it to use a faster dot product. You don't have to normalize it when you're doing a vector cosine. So it's very commonly used, and so it's a nice option, and it makes things really clean. And so I would like to adhere to that when it makes sense. So this is our vector memory, and then here's the output, and it's just a vector memory sum. And you can then retrieve things out of it using the inner product if you know what you're looking for. And so then we talked about the fact that we need a reset. And so we can just set the gain to the feedback gain to 0. And this goes all the way back to LSTMs. And this has changed a lot over the years. And we've talked about that a little bit. And so we also need an input gate. And I would say Mamba really illustrated that, because that was the big step forward for it. They call it selection, the selective state space. And so you have an input gate as well as a feedback gate that kicks in when it needs to, or all the time at some proportional level that's learned. And so this is how quickly you can get to a gated recurrent network. Just a few ideas. An associative memory that's just a sum of vectors, and then we have these learned gates. And so this is kind of where we were. And let's see, somewhere we talked a fair amount about this feedback, and I don't think we talked about this point, which is considering separating the activation aspects versus the feedback, because feedbacks are dangerous. I actually want to set it to 1 and then just do a reset and have this be very discrete, and just have it just reset at at some length, like in the end of a sentence or in the end of a paragraph, whenever we know we would like to reset it. We have this sort of notion of context buffer. So when you reach the context buffer size that you want, that's when it's time for a new context, then just reset it and just kind of factor this. So this is one of my experiments to experiment with memory duration and memory clearing. Whereas when you have this pole, we call this the pole, that's the feedback gain. You have to be really careful with it. And in something like Mamba and all the state space recurrent neural networks, you've got a kind of gain there that sets the duration. So you can think of it as an exponentially fading memory, and this pole, this feedback gain, determines the time constant of decay into the past. And so it's just modulating memory duration. And so I have a couple of ideas about changing that and implementing duration separately, and then sort of bringing back the activation. We'll see where it goes.
Julius, can I ask a question? When
Please.
you talk in terms of feedback, and it may be just, my visualization of it. But when you talk in terms of feedback in a sound system, it's that signal that just keeps, or is that what we're talking about? That it just sort of, infinitely grows on itself, I don't know if it's infinite, but you know what I mean. It just sort of
Yeah,
grows on itself over and over.
yeah, we call it an infinite impulse response filter. So if this input here is just an impulse, which
Hmm.
is just one followed by zeros, then well, it gets multiplied by G, and then it goes in here, and then it just circulates forever,
Got it.
unless this feedback gain is zero. And so we have the stability boundary, which is the gain of one.
Mm.
And that's actually where I'd like to put it. I'd like to put it at one and let it just pile up. And then another thing you can do is have a power normalization. I think you see this in the Hawk and Griffin um, system from Google DeepMind, where let's say this is zero point 0.9, then you would have this be 1 minus zero point 0.9. That would be amplitude normalization. And if you're
Oh,
assuming it non-coherent, if you're assuming that all the vectors that go in here are substantially orthogonal, then you want to do power normalization. And then this gain should be square root of 1 minus p squared. So there's
mm,
this natural tying between this feedback gain and the input gain if you want to normalize power or you want to normalize amplitude. And so in this case, I guess you want to normalize power because the space is really large, the vectors are normally orthogonal to a first approximation, and so power normalization makes most sense. And so you see that. But the Mamba breakthrough, I think, was this right here. And it might, I don't know how far back it goes before Mamba. It was somewhere in the state space series, but it's, here's your parameter that you optimize, and it's based on it's just parameter of x, y. So it's based on input. So it's a learned parameter, and it can do anything, go anywhere. And then Soft Plus makes it positive, and
mm.
that's your delta. They think of it as a time step for discretization, and then it's used as e to the minus delta. So your pole is e to the minus positive something, and they even add a little offset. So delta can't go all the way down to zero, and that means that e to the minus delta can't
Can't
reach one,
expand.
and that
Yeah,
means this feedback loop is stable. It's guaranteed stable. If you let the
interesting.
feedback go to one,
So,
then it rings forever. If you ever let it get greater than one, you've got your famous exploding gradient.
Hmm. Yeah, okay.
so just the
Thank you.
way that they parameterized it made it easier to train then, is that what you're
Right.
saying? Yeah.
Right. Yes. And we noticed that for decades. I mean, my graduate research was in system identification, and this is the kind of stuff we were doing. And the way we thought of it really was your loss function wants to minimize what really matters. And so in a situation like this, it would be like the decay time. It's like the decay time of a vibrating stream. You want to know, does it ring for 1 second or 2 seconds or 5 seconds? And that's the actual error. That's the perceived error. And so if you minimize that, then you end up going through, logarithms, exponentials, depending on which side you're on. So all this kind of falls out from just minimizing the error you really care about. But of course, the expression for that needs to be differentiable, but it is, and people are doing it, and backprop can handle it.
Hmm.
So that to me is another way that we learn this. So it's an important lesson, and there's multiple ways to get to it. And I don't know how the safe space people got to it. I don't know the story there. There was no, they basically just did it and documented it, and thank you very much for that. But there's no real
We're
discussion
not
that I
gonna
found.
we're not gonna give you the secret sauce, right? Or something like.
Yeah, the thinking, like in the Google DeepMind paper, the Hawk and Griffin paper, I didn't see anything about power normalization. What they were doing, cried out for mentioning this is the power normalized scaling, and that's the main difference between it and Mamba. So in Mamba, there is no power normalized coefficient going into the feedback. But the later paper for Hawk and Griffin did make that change, and they have a figure showing the difference as a result. It's very interesting, and it just doesn't feel fully discussed to me. It doesn't seem like it's, and that may be on purpose, right? I mean,
Mhm.
it's like we're going to publish so much, but not more, and we're not going to give away our, I don't know, I I
Julius, I
I
had a question.
what?
I'm not letting this go on yet. I have another question on here on this page. Um, you had said, if I recall correctly, you said you had mentioned associative memory, that this gives you an associative memory. Could you explain that in this context?
Yeah, the idea, well, that actually goes back to the embedding. So these vectors need to be a decent embedding. Okay. And so that means that if the vectors are close together, they're close together in meaning.
Okay.
And so the way you retrieve from this associative memory is with a dot product. So let's say you're looking for, the word apple, then you do the dot product of y and the apple vector, and you get a fairly large number. So you say, there's the word apple is in there. And now you come along and do a dot product with pear. And because pear is not too far away, you get a halfway dot product result. So you can get everything related to Apple by just lowering your threshold of detection in your perceptron. So we talked a little bit
Oh,
about using perceptron, and I'm coming back to that. I'm about to go to arrays of perceptrons, and we'll see it more then.
okay. So you weren't saying that providing this feedback loop, single pole feedback loop was creating an associative memory. You're saying within the embeddings kind of effect a associative memory.
Well, the
Is that what
embedding makes it associative, and the feedback makes it a memory. So the
okay.
feedback just piles up the vectors. It's just giving you a sum of vectors, but those vectors in order for it to be an associative memory, the vectors have to be clustered close to each other when they are close together in meaning. So the clustering, thanks to the embedding, makes it an associative memory. But it's a memory, even if you don't have an embedding, you just start throwing in random vectors. That's a vector memory. It's just that there's no relationship. There's no Euclidean geometry
Gotcha.
relationship, but it's a vector. So I don't know. So I guess the associative I would want to strike, right? Because
Okay.
to be
Okay.
associative, you need that embedding for the associative
Okay.
So
property.
this is a memory with a parameterized decay, kind of forget
Yes.
cycle.
Yeah. And
Yeah.
and for me, I think of this as one. I think of it, back here, because that's the way I want to do it. I just want to have a reset. In other words, I want my memory because I made this point. I think we talked about it last time that I'm going to get to it coming up. I'm going to get to an argument for why the feedback gain should always be one, and you should think of it as a reset when you need it,
Mhm.
even though that's not what's going on. But it's what I'm going to try to make work. I mean, really am going to this is what I'm running with, because it just was what makes sense to me. This is you know these vectors are on the hypersphere, so I'm only using unit norm vectors for my embedding, and I was really happy to find this optional argument in PyTorch that I can just ask for that and get it. I don't have to train that myself.
Right.
Or maybe I should train it myself if all it does is RMS norm the embedding without any training. I hope it was trained to be. I have to check that. But so in other words, I want my vectors on the hypersphere, and that'll be kind of a recurrent theme through everything I'm saying, because it's very clean. So you can think of it as, normalized signal processing everywhere. And this is a big thing in signal processing. So I'm biased by that. I'm biased by all my experience in normalized ladder filters, normalized state space filters. We could talk about that. Balanced realizations is the buzzword in the state space world. Normalized ladders are really nice. It's power normalization. It's really important numerically. So if you like, for example, in a normalized ladder filter, it's just a filter structure. This is a one-pole filter structure. It's a direct form filter structure. There's also other structures such as the ladder. And so in the normalized ladder, you have the property that when you feed in white noise, the variance is the same at every state in the filter. So it normalizes the state. And that's really valuable when you're stuck in fixed point arithmetic.
Mm.
And fixed point arithmetic is really important for minimizing the cost of these things. So if you want a minimum cost inference engine, you really do want to get it into fixed point, and you want to get it to the minimum number of bits. And so normalization really does become critical.
Hmm.
We have a couple of I see
Yeah,
Jana
let's go through
has
questions.
a question.
Yeah, so I guess what you're saying, Julius, is that it's sort of accumulative memory, right? You just keep adding your
Mm-hmm.
your sort of n minus one, n minus two, and so on.
Yes,
And okay, and so you
this memory.
mentioned yeah, and you mentioned the exploding gradient with the other, with the P and the Q. So I guess you could also explain the diminishing gradient. Could
Yes.
you, like with like, if P becomes close to 1 or something, or how
Yeah,
would you do
then,
that?
well, so in this case, the gradient doesn't explode and it doesn't vanish.
Right,
It goes forever. It's the eternal gradient,
right.
because
But in
it's
the
a
next
non,
one, I think,
yeah, when we do
in
have we have a
the,
gain,
yeah,
yeah,
this
this
one.
one, yeah. So if P is less than 1, so we're training it like this, and we have an offset for delta, then this cannot reach 1, so this will fade exponentially. So the gradient will fade exponentially. It's an exponential fading. So the best way to think about it really is just think of the impulse response. Take a 1, put a 1 in here and see what comes out.
Hmm.
And if everything's fixed, you'll get an exponentially decaying sequence.
Okay, yeah. And um, when you said pole, it kind of reminded me of 1 over z minus, some constant, z minus a.
Yeah.
So what does that imply here?
Yeah, we talked about the one pole filter. Let me find the one pole filter. Here you're talking about like this transfer function here, one over one.
Kind of, but even in the figure where you have the z to the minus 1, which is 1 over z, you could have 1 over z minus a, couldn't you? Or does that mean anything?
I'm trying to think of where we are. So
You were on.
Yeah, anywhere. Yeah, here.
okay. So how do you get 1 over z?
Here. So, like right now, you're doing 1 over z. Could you do 1 over z minus a, or does it mean anything to do 1 over z minus a, I guess, is my question.
Well, that sounds like a translation of the z-plane, and things like that are done. So z inverse just stands for a unit delay in this
Right.
system world.
It's some
So
z transform thing, isn't it?
yeah, it's the z transform of a unit delay. So the
Yeah.
z
Okay.
transform of a one sample delay is z inverse. And
Okay.
so
Yeah.
now if you do this, conformal map of z gets replaced by z plus a, then you've translated the points. Let's say a is real, then you've just translated all the points in the z plane to the right by a, and that has meaning. For example, a lot of times you see people do transform from the origin to the point z equals 1, and you get really nice numerical structures when you do that. It's effectively taking the z equals 1 point as the origin, and numerically, which makes it more like the S-plane. The S-plane is for continuous time systems. The Z. I have a little tutorial on S-plane and Z-plane. I could switch off to that if
Okay.
you want.
No, I mean, I was just curious. Like the S is like the Laplace
Yes.
transform, and yeah.
Yes.
Okay. Yeah. Yeah.
Right.
Okay. Cool. Yeah.
So,
Yeah.
so whenever things like that happen, and you get good properties, look at the match Z transformation for filter design, the impulse invariant. Look at all the different methods for going from an analog filter to a digital filter, and you'll see things like that going on. And you normally do that to achieve various objectives like better numerical performance, or maybe you're trying to warp the frequency axis that way. Stuff like that goes on. So yeah, but that's frequency transformations for some purpose, and so you have to inverse Z transform, see what that did to you in the time domain. So yeah, it's commonly done.
Yeah.
But
So you mean like right now? Go ahead. Sorry.
right now it's just a delay, and we don't need it to
Yeah.
be anything fancy. In fact, I thought about just replacing this by D. I was going to put like or delta. I was going to just I know that the system identification people use Q for the delay operator instead of Z inverse, and so that's really nice. So
Yeah.
it's
No,
just
the Z inverse makes sense to me. But yeah. Yeah. Okay.
it's always bothered me to have the inverse. I don't like it, but it goes back to
Okay.
Gold and Ritter. It goes back before Oppenheim and Schaefer and Rabiner and Gold. It's like the very, very beginning of digital filter theory, probably the 1950s. So it's very old, and it's just traditional to hang on to things once they get established.
Yeah. And and like you're talking about the S plane, the S space, and so who knows, maybe they'll come up with some, instead of neural networks with computers, you could have an analog version of it perhaps that could also
I
do
think
similar things.
Yeah.
I think that makes a lot of sense, actually. And
Yeah.
the most densely integrated digital, you kind of have to think of it as analog anyway, right? Like you're pushing
Mhm.
against the quantum limits. You're pushing against how fast you can charge these little CMOS capacitive nano things, and so
Mhm.
it turns into analog eventually anyway.
Right,
So you might as well start thinking that way.
right.
Um,
That's cool.
I think
Yeah.
that makes a lot of sense. Quantization, they're even looking down to 1-bit quantization.
Right.
So,
Mm.
so when the bit is 0, there should be no power, right? It's like a CMOS,
Right.
nothing flows, there's no memory, there's no energy cost whatsoever. And when
Right.
you conduct, you just are charging this extremely tiny capacitor. So that
Mhm.
should be very, very cost energy efficient. If you can really
Mhm.
get inference to work well at 1-bit quantization of the weights. I mean, that's the tricky thing. There are papers on it. I
Mhm.
haven't studied them. That would be a great thing for this group, to look
Yeah.
at 1-bit quantized inference
We do
engines.
have a few more questions, though, I see here.
Sure.
I don't know if you've
Cool.
looked in the
Thanks.
meeting chat. There's one from Kartik. That
Let
if you
me get
could,
the chat up here. Why am
or
I not
Kartik, do you
seeing?
just want to unmute yourself and ask
Well,
your
now I
question?
found it.
Okay.
It's up at the top for some reason. Let's see.
Right.
1 over z has a pole. 1 over z is a pole at z equals 0. So z inverse. So a unit delay is a pole at the origin of the z plane, which is kind of weird. And if you have 2 samples of delay, now you've got 2 poles on top of each other at the center of the z plane. And what does that mean? Well, in the magnitude, it means nothing, because you evaluate the frequency response, for example, on the unit circle, and so your distance is 1, so it's just 1 over 1. So the magnitude response of a unit delay or any number of delays is 1. So it's an all-pass filter, you can say. It's a very trivial all-pass filter. But what's interesting is the phase. So as you go around the unit circle, you've got a phase. 1 over z inverse becomes e to the minus j omega t, where capital T is your sampling interval. And so that's what you see as you go around, and that corresponds to a delay. So in the frequency domain, I think of the z plane as a frequency domain. Your delay is the slope, the negative slope of the phase. So e to the minus j omega capital T is a slope of minus capital T. It's viewed as a function of omega. And that's one sample of delay. That's
Julian, you're
unit sample.
you're not sharing your screen anymore. You're
Oh, really?
somehow.
What are you looking at?
Oh, okay. There you go. I think you must have hit the meeting chat thing, and it probably flipped it over.
Yeah, I went off to the chat because I wanted
Yeah,
to.
yeah. No, we've got a black screen now, so we have to
Oh,
be a
that's
little more.
terrible.
Sorry about that.
Zoom. Okay.
Yeah, it's just it's a feature of Zoom. It's not a bug; it's a feature.
Yeah, yeah,
Okay.
that's fine. I would leave it sharing. I mean, you had it shared, and I don't
Yeah.
know.
Yeah. Okay.
So anyway, so this is so that was just a little mini tutorial on what Z inverse means. It's a pole at the origin, and it does have an effect on time. It's a time delay. And so and if you don't have the inverse, you have Z, then now we can say we have a pole at infinity. That's one way. So it's really convenient to think of the Z-plane as, the extended sphere. Is that the Riemann extended? So you just add the point at infinity, and it's topologically equivalent to a sphere. And then Z and Z inverse, it's just an inversion with respect to the unit circle, and it's a nice, well-behaved conformal map. And a lot of times that's what you want to do is take your system and substitute Z gets Z inverse, and then everything's get a lot easier to deal with, and then you can put it back later. And so this kind of stuff goes on all the time. And that's how you interpret it on the unit circle. So the unit circle is your frequency response, and we can talk about that. And that is, kind of the main thing that's taught in Music 320, which this talk was originally prepared for, to just try to show them a path to neural net architectures in terms that they've been taught already. And so that was sort of the agenda with the original version of this 15-minute talk, which maybe it was more like 18 minutes.
Okay,
So,
well, let's
and
move
that's all
on.
I would. Yeah, any more questions?
Ted had
No,
his
I
hand up.
meant it in terms of the closed loop transfer function, not 1 over z by itself. That, yeah, I guess it's well, pole at 0, but in terms of the what the transfer function would be for the overall system, I was asking whether that means this is because of this 1 over z, you create a pole at p. Because I thought that is what you had in one of your early slides where you didn't have the dependence of p on xn, but just as a single scalar parameter, I guess.
Ah, yeah. It starts out as a scalar. Now it's an array of unit sample delays. It's just a vector delay thing. So here's where everything gets summed, and then we have to take that sum and we have to hang on to it so that we can add it to the next incoming vector. And then we get a sum of everything we had before plus the new thing. And then, so this is just saying delay it to the next time step. And really a good thing to say right now is that Z is not an option here. Z is not valid because Z means you have a Z transform. And to have a Z transform, you need a linear time invariant system. Every one of these coefficients depends on the input, right? So that is the very definition of a nonlinear system is when your coefficients depend in any way on your input signal.
Okay, maybe we
This
can
is a
move on
it does not have a Z transform. What?
maybe we can move on to the where we're trying to get to, I think, a little bit further down.
Okay.
If you don't mind.
Yeah. Don't push me too hard on the signal processing interpretation here in the Z-plane because it is not an option. Although this is really just a delay, and a delay really does have a Z transform, but we then can't compute the Z transform. We can't compute our transfer function because we have a nonlinear system. So there's no such thing as a transfer function here. There's no such thing as a frequency response unless you want to tabulate it for every possible input. So say goodbye to the frequency domain, say goodbye to the Z-plane, the S-plane. Maybe you're happy because you never wanted to go there anyway. Most of my students go that way. So the good news is we don't need it because we can't have it.
Okay.
So that's, but the structure is very familiar and there are, time domain normalization and quantization benefits that have been learned, hard earned over decades, almost like half a century more. And I think some of that could port forward to the machine learning domain. I think that's why it's actually useful. Okay, so moving on. So we got an input gate, we got a feedback gate. Why not an output gate? So if we have an output gate, that'll just clamp it down to 0, which suggests, well, maybe we would want to instead just feed the input around. So when we don't want the output, the C vector here says, no, let's not use that. Then we'll just pass it on through. And of course, based on what I've been saying, you would expect me to have a power normalized gain here. So this should be, essentially 1 minus C squared in this path. And so that would be what, my theory would suggest. But we know better, right? We know that the residual connection, that the skip connection doesn't do that. And so we need a reason, we need an idea that will make us invent that. And so here's the idea. This is the best I come up with. Don't scale the bypass and use RMS noise norm at the input of the next layer so that a bad layer, so there's no way a bad layer could isolate deeper layers from the input. So if this thing goes crazy and it's just putting out garbage, and the gain is, let's say, 1 for everything coming out of here, then the power normalizing gain here would be 0. So it'd say, wow, this thing's really confident. We're going to pass this through, but we're going to have to shut off everything coming in because we have to normalize power here. That would be bad if this is not good coming out, right? So it's like a hedge. It's saying, we don't even trust this network. Not only do we want to turn it off, but when it knows that it's bad, but if it doesn't know it's bad, we might still turn it off. So that's kind of the thinking there.
Julius, it
feels
like those are kind of equivalent though, because if C became very large and you had an RMS norm after it, it'd still squash the input, right?
Well, except that it does have a skip connection, right? And
But it skips, if the skip connection was added to a very large number, if C was very high, and then you did it, you normalized it after that, you essentially are ignoring the input.
yes, but then it keeps going. So in other words, yeah, you'll still you'll give a very large input to the next layer. It gets RMS norm after the skip connection is added, but that RMS norm happens after the skip connection is forwarded. So you know, it could still decide to recognize, oh, this is garbage, and clamp it down, and then not continue putting out garbage, and then its skip connection would save all the early layers because it hasn't been squelched. There's no way to squelch the input from early layers, you know, because you know the RMS norm happens after the next branch for the next skip connection, right?
Mm-hmm.
I actually have an example. We can go look at some of these. So the usual thing is, let's see, I'm trying to find one. I just have these lying around here. So here's the RMS norm. See, the RMS norm happens after the skip. So you can always skip around.
Oh, I see.
There's a skip that makes it all the way out, no matter what. But yeah, you're right that if this
skip
puts out
takes off.
really,
So what you're saying here, this picture clarified it for me. So the skip takes off before the next RMS norm.
yeah,
So
yeah.
okay, got you. Okay.
So yeah,
That's
so
my question.
let's see, where are we here? Let's see, what are we doing here? Okay, so skip connection. And yeah, and I am a little shaky on all that. I mean, I'm not saying I'm not ready to like publish this or anything. In other words, anything, this is just a way of thinking. This is just a theoretical framework that suggests things, and it gives at least some motivation for what's happening. And then it also gives motivation for trying some different things. And then those have to be tried out and tested. And that's what I will hopefully get to, and get some results on some small synthetic data sets, and publish a paper, and maybe it survives, maybe it scales, maybe it doesn't. Okay, so next idea is state expansion. Okay, so the motivation could be, well, you know, if we made this bigger, we could put more in, you know, so it's, you know, we could increase our model dimension, but maybe our model dimension is adequate for the vocabulary that we have. And so we want to store more stuff, but we don't want to necessarily increase our model dimension. Well, let's just use more of these delay elements. And so that's the basic idea of, you know, expanding the state. And this is terminology used in the state space framework. And then I went ahead and just put a state space, a complete state space model here, which sort of generalizes this. So instead of a gain, we now have a B matrix. That's your input matrix. It's also in its learned. And then we have a general feedback matrix A, and we have any number of model dimension delay elements here. It's just think of it as a concatenation of any number of these vectors. And it usually has the label H sub n for it's the hidden state. In machine learning, it's called a hidden state. But in a state space framework, it's just, you know, it's just the feedback delay in the discrete time state space. And then we have an output matrix that you know, generalizes our output gate. And then we have, in state space, you also have a direct term, and we just argued for getting rid of that and making this one. And so, but it's here in the general state space case, it's the direct term. So the state space model, the dynamics don't have a direct term. There's always at least one delay. And so I can see now that this is not written properly because the C matrix actually has to hang off the output of all these delays. You can't have a C connection to the direct term here. So this is an error in the diagram. I'm going to have to fix it. I'm going to have it, I think what I'll do is have it come out like A does. So this arrow will come out here, and then there'll be C, and then it'll go out like that. So yeah, there's an undesirable direct connection there. So this is just trying to bring in the standard state space formulation. All right, so I think the grand, you know, wizard of state space these days is Mamba. and Mamba 2 just came out, which is almost identical, just a little bit of change. And it seems to be mostly about cost reducing it, making it smaller and cheaper without sacrificing quality. And so if we do the state expansion, we get increased storage capacity, and we've learned from the SS, the state space community since S4D or so, that you can really just use a diagonal state space matrix. So really, it's not a full matrix here. You can really think of it as a parallel group of RNNs, like we had up here. So it's like the one pole case, just multiple of them in parallel. And so it's gated state expanded RNNs. And
Julius,
so, yeah.
sorry to keep jumping in, but so
No,
do I
please.
read from this the key point that HN has a different dimensionality than the XN and YN? Is that correct? Is that what that's saying?
Yes. Yeah.
Okay.
So the dimensionality of X and Y are the same as this Z here. So that's our original
Okay.
model
Okay.
dimension delay.
But
And
HN
then
is multiplied it. Got it.
Yeah. And I believe Mamba only uses 2 of these. I think it's only a 2x state expansion. And I do have Mamba here. Let's look at Mamba real quick. Yeah, so here's the input. It gets up projected, and I think it's just 2x from the model dimension to double that. And then they have this interesting, I think it's a 3-point convolution, which just does a little bit of mixing for you. And it helps, it's better. And we need to figure that. I don't have an idea for that. I don't know how to motivate that. And I really don't know how to motivate this activation here. That really surprised me. From my point of view, maybe you would have an RMS norm or something, but an activation, that seems really like a lot of change going into your SS. So your SSM is driven by the activation output here, which is quite severe. And this is more reasonable because this is an activation for gating. And that totally makes sense to me. But for the input to the SSM, I would actually, I have it on my list. If it's not, it's going to be on my list to try replacing this sigma with an RMS norm, see what that does. Because it's just once again driven by a particular intuition that may or may not make sense, may or may not work, right? You never know until you try it. Let's see, where are we? Oh yeah, it's up here. State expansion. So this is our state expansion version, and we need that to get to things like Mamba. And this is one of the main changes in Mamba 2, that not only is the feedback matrix diagonal, but it's a constant times identity. In other words, all of the little parallel RNNs have the same exponential fading memory duration, which I think is very, very interesting. That's really quite interesting. So they all, shrink or grow together. And when you get P close to 1, then you're asking for a very long memory. And when P gets small, then it fades. And what I really want to see it do is just toggle between 1 and 0, because when it's 1, it's just accumulating memory and it's not doing any amplitude scaling. And then when you want to flush the memory, you just set it to 0. So those are the kinds of experiments I plan to do. And this is just a little side note that the gating matrices are simple linear input projections. So you have your input here, and you go through a linear projection, a linear layer that, not a linear layer, just a linear projection. It's just a matrix multiply that gives you your, but it's a learned matrix that gives you your B and C matrices here. And so that's just something I saw. I like to look at the Mamba minimal code, if you've seen that. The Mamba code is great, but the Mamba minimal code is a little more readable. And I think Sasha Rush wrote that and has a nice YouTube video about it. Okay, so let's just continue the ideas here. I should watch the time. Yeah, we're okay. So detecting multiple vectors in parallel. So we're just sort of building up our ideas to try to get to what's going on. So we want to basically do memory retrieval in parallel. So we talked about using a single perceptron to detect the occurrence of a query vector, which is the weights of the perceptron in the memory. So you do a dot product, and if it's greater than the bias, then it fires. You fire the neuron, say, I see my vector. My weight vector is in your vector memory sum. And so that's what comes out of one perceptron. So let's just have a bunch of them. And now we get a weight matrix, and we get an array of activations coming out of that. So that we need that, right? So we have a set of outputs, y sub I, and we have a set of weights, and they all dot with the hidden vector to give us a detection, vector cosine, because everything's normalized now. This is vector cosine without any kind of denominator, and we just have to compare it to our threshold, which is between 0 and 1, and it's expected to be around 1 over n, or 1 over square root. It's 1 over n if it's if it's not there, if it's just random. So that would be like this looks like a white noise vector compared to the memory, and so you see something like 1 over n. But if it's like 0.9, then we know, hey, that's really in there. And if it's 1, then it's like you nailed it. You went right on. But if it's like 0.9 or something like that, well, it might not be the vector we're looking for, but it should be something that means almost the same thing. And so by setting this threshold, we can control how similar the stored vector has to be to the query vector. So that threshold gives you that control. How similar, how large is the neighborhood we're willing to search. And so this comes up in RAG, right? So if you're doing retrieval augmented generation, then you're trying to set this to get the right degree of similarity. Okay, so that's that. And then in the state space model, you can get these weights right out of your C matrix. So that's a reasonable way to think of what it's doing. Okay, so then we can indicate. So then, okay, and now we need the idea of training this whole thing when it's all stacked up. So we've got this array of activations, and if we are going with perceptrons, those are just signum functions, right? They just they've got sharp corners, and you can't really train through that because your gradient is either 1 or I guess it's just 0 everywhere except for getting an impulse at the origin. So it's just not a valid. You don't get a gradient out of a signum function, and so I still don't know who came up with it. It sort of seemed like it came up at a conference or at some kind of meetup, and then everybody went off and did it. There was just this buffalo herd of people. Everybody, because the neural net research did get really revived in the 80s, and so a lot of people were working on it. There's a lot of government research spending going on at that time, and so a whole lot of labs were doing it. And so I just think it was some Asilomar conference that the idea was passed around, and then all of a sudden it just emerged. Everybody's doing it. But it was critical, right? Because that's what enabled deep learning. That's when you can now differentiate through the output of a perceptron, and now you can stack them up in layers. You can differentiate through the whole thing, and they call it backpropagation. So, gradient descent was well understood. The LMS algorithm had been going on for 30 years or something like that, and so it was used all over the place in filter design. Gradient descent was used in system identification. It was all very well understood. But what was not understood until the 80s is that, we can differentiate, we can do gradient descent on a neural network, even a deep neural network. And so that just kind of blew the lid off of everything. And interestingly, the training algorithm for the original perceptron is gradient descent. I mean, they figured out how to do it. They didn't differentiate, they just wrote down the gradient and did it. And so that you can think of it as the LMS algorithm with a kind of a switch. So it was, I think the concept was thoroughly available, but the breakthrough was changing the activation from signum, just a little square step, to something soft and differentiable. And I think they started out with 10H, and then ReLU. ReLU is really nice because your gradient's either 0 or 1, and that's a very clean set of gradients. And then all sorts of things have come along. What is it, CLU and all these things. They know now that they've got ELU, they've got you've seen all these variations, and it
Right.
seems like what you want is something smooth, looks like Rayleigh more or less, and it has a little bit of a depression around the corner, which, you know, when it changes from 0 to 1, and that seems to be to just kind of hang on to things, keep the iteration around there when it wants to be around there. And I've learned from, you know, some a video by Andrei Karpathy that that's kind of where you want things to be when they don't know where to go. You want them to be poised to be able to go either way. And so it seems to provide a bit of a bias for, you know, staying around there where, you know, let's wait until the training tells us whether we want to go up or to the left.
Okay.
So anyway, that's just a little bit of a historical observation there. Okay, so now we want to do sequence modeling. So we've got this vector memory, we've made it deep, you know, we've got this big neural network, we can do pattern matching, pattern recognition, but now we want to do sequence modeling. So we have to have some notion of a sequence, and it's not there right now because right now the vector is just a pile of I mean, our vector sum has no ordering, right? There's no ordering in a sum. So a vector sum you can think of as just a bag of words. So we have to introduce sequence position encoding. And so the only thing I can see going on in an RNN is amplitude decay, right? So you can say that there's a forgetting factor there, and so that's learned. And so you can actually, I don't know, you know, how, to the extent to which neural nets are using this, but you think they have to, that or maybe they're just getting by just knowing that all the words are present and we don't know what order they're in. But there is information there, and it's the amplitude decay. So the smaller the amplitude, the more the match, right? I'm sorry, the smaller the amplitude, the older it is, and the smaller the amplitude, the less similar it is. So that's conflated, and that's why I don't want to use it. I don't want to use amplitude decay. You know, as somebody who's just trying to reinvent everything as signal processing, I don't think it makes sense, because you have angular distance on the hypersphere conflated with age. It doesn't make sense. But it's not the only thing we can do. We can also do sinusoidal amplitude modulation, and that was what was used in the original transformer. So you just you do AM like any AM radio. And then more recently, people are doing you know, what they call ROPE. It's rotational positional encoding. And so in our context, we can multiply the vector sum by e to the j delta. This is just, I mean, you can also do a cosine matrix. I mean, what they really talk about in the paper is a matrix that has, you know, a 2D rotation matrix along a band. But, you know, an elegant way to express it really is just now introduce complex numbers, and Mambo supports complex numbers. So we can use the complex number support in Mamba to implement ROPE. So we just multiply the sum by e to the j delta, where delta is our phase step that we want to associate with time, and it's limited, right? It's going to run off the end at some point. So we have to decide what our length is. Let's say L is our sequence length. Then delta, we can set it to 2 pi over L. And then we get L steps before we come back around. So the aged version of the hidden state is e to the j delta times the unaged. So this ages at one sample. And so, and then it goes, you know, it's recursive, so it'll keep happening. So, so it just keeps twisting around in phase, and it doesn't come around to the original phase until the end of this sequence, which is at most L. And so at L, that's when we're going to reset the memory. So we'll just have a 0 feedback gain, because we know we can't encode any more time than that. So it's just reset time. But you can do better, and this is inspired by the bilinear transform in filter design. We can use warp ROPE, and so instead of just a linear phase step, we can have a phase step that decreases with time. So early on, it's 2 pi over L. So it starts out looking like this previous one, but then as you go up, it will never approach 2 pi, right? So in the limit, as n goes to infinity, you approach 2 pi, but you never get there. So that's very much in the spirit of a bilinear transform, for filter design, which takes the S-plane frequency axis, which is infinite, and maps it to the unit circle in the Z-plane, which is finite. And so everything's fine at low frequencies where the map is fairly linear, but as you go up towards half the sampling rate, it gets compressive like this, and you never make it. So infinite frequencies are mapped to Z equals -1. Roger has a question.
Yeah, just a quick question. So, rope versus the sinusoidal positional encoding. The sinusoidal, is that added to the embedding? Add to the vector? But
No.
rope actually multiplies it, huh? It's a multiply instead of an add.
Yes, it's a rotation of the embedding instead of adding a sinusoid to the components of the embedding.
Got it. Okay, I didn't know that. That's interesting.
Now I should review that. I haven't seen that in a long time. I should review that. Yeah, yeah. If there's anything, I'll review that, and if I have any mistakes, I'll bring them up next week.
Okay.
I think that's right. Does anybody know otherwise? I think it's really just a rotational. Well, it's a cosine sine matrix. I have the paper. I could bring it up. But
No,
if
that's okay. I just never read it. I didn't understand that nuance about it. So that's cool.
Yeah, and they're not using complex numbers as I recall. It's really it's really just a 2x2 rotation matrix along a diagonal. So they so you imagine the coordinates of your embedding. See, let's say you have a vector that you're embedding vector, then you multiply by a matrix that has little 2x2 rotation matrices, cosine, sine, cosine minus sine. And you also do something you divide your coordinates in half. So, in my case, I just go from real to complex, which gives me twice as many numbers to work with. And what they do is take the real numbers and cut them in half and get the same result.
Yep.
Okay.
So that's coming back to me now. So anyway, and here's a little fine point. I think this could be a paper, if anybody wants to work on it, you can have the idea if you want. I mean, I would love to get around to all this, but I don't know when I will, but I would love, it's ongoing, let's say, and you're welcome to take it over. So here's a blend of uniform and warped rotation. So you start with uniform up to your expected sequence, your typical sequence length, and then you go into this compressive, never going to get there. So you can handle any age, but you're more spread out over the typical age. So this would be, a blend of uniform and warped. And I think it's good to be uniform because you have more space during recall. Things are more separated out. But I don't know. I think this is really worth trying. So I have these benchmarks for testing memory. I'm going to try this out.
You could
Hey,
also,
Julius,
Yeah.
a quick comment about the different embeddings on the previous slide. I understand how basically you're like chopping up, say like one full circle into bits so that you can represent the different positions. The one thing though that warped rope and the bottom one might not do as well is that your model actually wants to be able to do position arithmetic. And position arithmetic is possible with these, but it may be much, much more complex. Whereas since we're just doing matrix multiplies, if you can do linear operations for position arithmetic, that's going to make life a lot easier for the model. So while conceptually, I totally get what's going on here, practically a model that's made up of a lot of linear operations, a lot of matrix multiplies, may have to consume a lot of compute in order to just calculate position math, which might not be optimal.
Well, how does rope do that? So how does rope do positional calculations? Because I see this as equivalent to rope.
Yeah,
And
so basically, if I have a matrix that's just e to the negative delta, right?
Mm-hmm.
Then basically I can go and I can say I want the previous token.
Mm-hmm.
All right. And if I know I want an item that's 2 tokens ago, then it would just be e to the negative 2 delta.
Mm-hmm.
Right. So if I learn those, then I can multiply by those, and I can get for the previous position. With like warped rope, I can see clearly there is a formula, like I can do it, but it may be a lot more complicated for me to say the previous token relative to me depends on where I am now, and I have to do a more complex calculation in order to get that.
Mm-hmm. Mm-hmm.
Ted, it might work if you think of it as kind of a piecewise linear, though. You might say, you know, if it was a long time ago, its scale of earlier is different than if it's just a little, you know, a few tokens ago.
Yeah, no. I'm saying mathematically, it's clear to me how this could work. What I'm saying though is that if you just want to be able to say previous token and then match on that,
Yeah.
warped rope, you need to know your absolute position in order to accurately calculate previous token. In rope, you don't need to know your current position, absolute position, in order to calculate a relative offset.
Mm-hmm. Yeah, because if you're far back, if your position is, let's say, distant past, then your neighbors are very nearly the same phase. So the phase increment to your neighbors has shrunk.
Mhm.
You need to know where you are. You need to have some idea of your own age before you can calculate distance to your neighbors.
Yeah.
But that'll be more of an issue for older tokens,
Mm-hmm.
not recent tokens, right? Because it's the
Right,
scale
but if
changes
you,
basically the
but if
longer you
you,
go
if
back.
if you do something like, say, this is a Wikipedia article, and I'm trying to refer to previously when you defined something, or
Mhm.
or you know, the example from Transformer circuits where they had Harry Potter, right? And so they were like, when you see pot, then the token that came after it was Tur, or I believe the other family name was Dursley, and that was, I think, 3 tokens. So when you see capital D, then the next token is likely Urs, and then the next token is likely Lee. And so to be able to sort of say, like, the token after D, you with rotary embeddings, you don't need to know whether D was 3 tokens ago or 3,000 tokens ago. It's the same math.
Mm-hmm. Yeah.
Does
Processing
that make
over a
sense?
time scale is not invariant. You don't have this shift invariant processing anymore.
Yeah. So again, I'm not saying that this cannot work. I'm just simply saying that how much of your model will be devoted to computing positional stuff if it's more than just simple linear type thing.
Mm-hmm. So does it work out okay in the RNN case? Let's say you're in an exponentially fading memory, and now you're trying to retrieve a token and its neighbors into the past. Now it's an amplitude that is not as different, but it is a relative. The relative amplitude is the same, but you know the ratio of amplitudes is the same. Here's the phase differences that are the same. The relative phase difference is the same here, but in RNN it would be relative amplitude. So it seems to be
So
doing that.
so my understanding is the original transformer paper, they had the sinusoidal embeddings, but first there were multiple of them, and it was not actually an amplitude modulation. It was conceptually a concatenation. So it
Oh,
was
really?
basically storing augmented dimensions with position information. It may not look like that when you look at the code, okay, but but at least that's my understanding, is the conventional wisdom is that those dimensions we were expecting the token meaning information, the grammatical and word meaning information, to be largely orthogonal to all of the position embeddings, so that you can essentially consider the position embeddings to be using unused dimensions in your space. And so then basically, if you simplify it and say that the word is on the left half and the position's on the right half, right? Then basically, if you want to know, is this similar to the word apple, then you just you mask off the left half and you compare, right? But if you want to know, is this one token before me, then you mask off the right half and you do some particular to say.
Yeah.
That's not maybe literally how it works, but conceptually, I think that's how people think about it.
I think that makes sense. In AM radio, you think of that way too, right? That's why you have so many channels, but each channel, you hear it at baseband. And so, so it's like each new channel gets its own region of frequency space, and it was previously unused. So you have this baseband, your whole vocabulary lives in that baseband, and then you add a sine wave that shifts it, so your other channel out to a whole new copy of the baseband. It's like new vector space out there. So that's analogous. And here you're just it's doing a phase rotation, and so you can think of, like, you maybe want to have your vocabulary in a cone of the hypersphere, right? So it's like your whole vocabulary is just occupying this one little patch, and then you multiply it by either a delta, which moves it over to a whole new patch. It's the whole vocabulary one sample ago, and that if your space is big enough, that should work out. If we can pack the vectors in there that much, but we have to be able to pack them in there, right? But yeah,
I can't remember, Roger. I don't think in this meetup, I don't think we talked about the what was that paper called? The indirect object identification paper.
Wow,
We talked about
I'd love to see that.
Yeah, so it was interesting that in this indirect object identification, which has this nice abbreviation IOI, in the IOI paper, the problem was small enough that they were actually able to do a bunch of trial and error and basically figure out which signals were flowing through when they did sentences that had two subjects. It was always a male and a female subject, each with single token names. Okay, so it's John and Mary, and it's whatever, Bob and Alice, and blah 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 blah. And so they purposefully constructed sentences of the form where so and so did blah blah blah, and then somehow it was like, then John gave the ball to, and then the logical most likely completion is her, because if there's only two people in this sentence and John gave something, then it would be to her. But if you flip it and you say blah 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 blah, then Mary gave the ball to, then you would assume it's him. So this is the indirect object that they were trying to see, that these models were getting it right. They were getting the pronoun right, but how did it know which one to use? So there was some interesting stuff going on in there where ultimately they figured out that there's times when it literally is using like position data as the main part of the calculation. So I don't remember the details, but the model was literally doing position arithmetic, and so that was that was kind of cool to see. Like, we assume it's doing that because it has to know the sentence order of words, but that was like nice to actually see like concrete. Again, sorry, I don't remember the details, but here's where we do blah 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 and calculate.
Yeah, I'm gonna try to find that paper.
Okay.
Julius,
Okay, well, I think I'm gonna run out of time again. This is fun. My 15-minute talk has spanned 2 sessions already. Maybe it's in the last 5 minutes, maybe I should just summarize the remainder and then we can talk about whatever we want. And so the next topic is, well, if we're doing rope, that's basically reserving one angular dimension for time, for age. And so, I have a very strong interest in reserving other angular dimensions for other meanings. And so, so we can reserve the radial dimension for normalization by, for similarity scoring by just simply doing RMS form. And then in the rope case, we just know what it is. We just impose it. But what if oh yeah, this is just some ideas about how you might get some more angles to play with, analogous to the complex phase. Thought about quaternions, and then you can go beyond that with the Cayley-Dixon construction. So you can get, you can get a lot of angles that way. And then this is just mentioning that everything's easy in polar coordinates. You can just right protect the dimension you want to protect. But then you have to propagate through, so you have to rewrite your back propagation for polar coordinates, which sounds hard and possibly like a bad idea. And so you can look into constrained gradient descent. There is a lot out there. There's a lot of projection-based constrained gradient descent. So that can be done. But what I think is really simple that I'm going to try is or this is not it. No, we're just using the fact that the MLP is it's just a general function, right? So you can train an MLP that will unrotate. So it'll take your current state, you add your gradient, and you don't want it to rotate along certain angles. So you just have an MLP that puts it right back where it was along those angular dimensions. So if there's some easy way to find that MLP, that would be great. But here's what I want to use. It's just a reserved translational dimension. So it's just outside of this whole, unit sphere world. And I've got a funny little new name for it. And so you just don't use RMS norms. So these are like side dimensions. And surely this has been done, but it's just side dimensions that don't participate in the RMS norm. And they're really just there as conditioning signals that you have total control over. And they just translate the space, rectilinear translation. And to me, that's very appealing for a new control dimension. So I'm thinking about that. Has anybody seen anything like that? I know I was going to just summarize, but that's one of my questions. I got to get my questions in. Well, we can come back to it. If anybody please tell me if you do see, well, I'm just going to do it, but tell me if you've seen the papers.
I kind of have a question. When last time we talked a little bit about superposition, Ted forwarded a really great video that covered some of that. But so the idea was, how did you express it, Ted? If you have a dimension n, it's something like e to the n different sparse features that you can represent with that, right?
Yeah. So in RD, right, where you have D dimensions of real numbers, you can only have D perfectly orthogonal vectors. Okay. If you have up to D things that you're trying to represent, you can represent them with zero interference. So as long as you can record them perfectly accurately, which, for example, floating point numbers, they're not perfectly accurate. There is some imprecision there. But hypothetically, if you can represent them perfectly accurately, then you can read everything out with absolute 100% perfect precision. Okay. If you want to represent more than D things, you're up the creek if you're using orthogonal representations. Okay. But I do not know the math. This is just what I read in the paper. It said that you can actually represent e to the d power vectors in RD that are almost orthogonal. I don't know what the definition of almost orthogonal is, but basically, yes, in high dimensions, any two random vectors would be close to orthogonal. But I think what they're saying is that like you can pick an epsilon, and like less than epsilon, these vectors will, their inner product will be less than epsilon. And so these vectors are very, very close to orthogonal. And then the idea is that you can represent obviously many more things. E to the D is exponentially more than just D concepts, right? But you just run the risk that you might get two different concepts happening at the same time. And then if you have this vector and they're not orthogonal, then when they're both present, what you're going to see is the sum. You're going to see sort of the midpoint between the two of them. And in an orthogonal representation, the midpoint between two things, when you project onto those separate dimensions, you still get a perfect readout. When you're using non-orthogonal representations, now you run the possibility that in between means something completely different than the original. And so there's the diagram from the toy models article that shows you the pentagram, where basically if you represent 5 things as a pentagram and you have things that are 2 apart, exactly 2 apart, when you have both of those present, then you'll just wind up with the other arm of the pentagon that's like, or 5-pointed star, that's exactly in between them, and you'll get a perfect signal corresponding with this concept, and you'll get no signal corresponding to either of the two. So it's not that you get some noise. Yes, that's why it has to be sparse, so that the odds of you seeing those two at the same time are extremely low.
So kind of trying to get my head around this high dimension thing. I understand superposition. You can kind of add these two numbers and these two vectors, and both are actually present. You can extract both of them. But I'm just wondering, when you start thinking, Julius, in terms of angular dimensions, or in the case of rope where you're actually doing angular modulation, do you still get that same preservation of like where you have the same superposition? You can like rotate it, and then yet the two vectors are still close if they were close before, or I'm having getting my head around this angular dimension concept.
No, so can I try this one, Julius?
Yeah, take it.
Yeah. So for simple rope, basically what we're saying is we're reserving 2 dimensions for angular information. Okay, and that in this plane, let's say we want sequence lengths up to 10,000. That 2 pi over 10,000 is ultimately what means something in this plane. Every 2 pi over 1,000 is 1 more token. So in fact, even though you have 10,000 different clock positions in this plane, there's only one concept, which is 2 pi over 10,000 means 1 token.
Okay.
So if you're at pi degrees apart from something, that means that you're 10,000 tokens away. I'm sorry, 5,000 tokens away, because you're halfway around the circle.
And what I want to think of conceptually is that my entire vocabulary is in one delta. So in other words, I can, when I rotate the space through delta radians, I get a new empty space that there's nothing going on in, that I can now populate with my entire vocabulary, whatever it is. And so that means there's no interference at all introduced by the rotation.
Right. What we're not talking about, Roger, is if 2 pi over 10,000 is our delta, we're not talking about saltiness is delta, sweetness is 2 delta, blueness is 3 delta, maleness is 4 delta. That will not work, because then when you just get something that's 6 delta, well, what does that mean? Is that 5 delta plus 1 delta, or is that 2 delta plus 4 delta? I have no idea what that means.
Right.
Okay. So we're not talking about representing unique things at each clock position. We're really just talking about representing one concept around in a circle using 2 dimensions.
So Julius, in your concept of the cone that shifts, the whole new vocabulary that's 1 delay behind or 2 delays behind, when I start thinking of warped rope, I start getting smaller and smaller shifts, right?
Yes.
You get to a point where there's like not enough room left in your little pie to represent your vocabulary.
Yeah, they're going to start overlapping. Absolutely. Inevitably,
Right.
they're going to merge. And so you get infinite memory, but the memory gets fuzzier and fuzzier. And if you're retrieving from that region of the space, this really, really long ago, you're actually going to retrieve anything that was near that same time, right?
You need
Anything.
the older it gets, the more precision you need to your floating point to tell the difference between 2 adjacent items.
Right.
Gotcha.
Or you could extend your model dimension or extend your state expansion and just give it more representation.
More space to work with.
Yeah. In theory, mathematically, it resolves, but in practice, you need that much better floating point accuracy for things
What I like about it is that it never wraps around. I don't like the regular rope because it comes around right back in your face. So L samples ago is now.
Right.
It aliases in time.
So Julius, in your example, you talked about having a combination of linear and a warped representation. Would it make sense? I mean, is there any reason that has to be binary? Could you just have warps at different rates that you represent things that a long time ago you have better resolution, kind of that type of thing? Or
yeah, there's an infinite set of possibilities here. You can set any kind of mapping you want. These are just some simple first order suggestions. First. Just one compressive warp. This one is linear followed by compressive, but it could be linear followed by reduced resolution linear, and you could like step down the resolution. There's just all kinds of things possible here.
And I wonder if the representations that we have right now don't care about time. They're all current words, right? But maybe there's different words that are more important to differentiate when they're older rather than new. I don't know. I'm not sure if that makes sense.
You could age different parts of the vocabulary differently. That's interesting.
Well, just so that they stay unique. Yeah, in the older they go. But then again, I guess what you said is expand the hidden state more, and maybe that takes care of it. If you need reference further back in time, just get a wider state.
Just enlarge it so you're getting good results.
Right. Yeah, and so from a representation perspective, I think it's clear. What I was saying earlier is that the question is, can the model learn to use these representations and do arithmetic on these representations?
Right. Yeah, that's critical.
Let me interrupt here. We are 10 minutes.
We're over time.
Yeah, we're 10 minutes over. Julian, how much more do we have on this?
Well, last time I already summarized my attention stuff, so I'll just rely on last week's summary for this summary. But I'll summarize what I newly added. Okay, so that'll be the only new thing here. So this
can I suggest we just pull it up next time, Julius?
Yeah, that's what I'm wondering. We're in a good point on this.
We might have to wait until I get back from a trip, but I have to look at my calendar, but yeah, I can maybe go next week, but I'm not sure where I'm going to be. So, but I guess I can do it on the road. It's possible. But let's just say at some point I would like to give a continuation to talk about the ideas. I think the ideas leading to transformers are interesting, and you can unify transformers with gated RNNs. And here's my grand finale diagram, which is a transformer which looks like an FIR filter the way I'm drawing it. And then this would be my, artist conception of Mamba or Mamba 2. It's basically 2 vector RNNs because it's state expansion of factor of 2. And so your transformer just sort of feeds right into your Mamba, basically. And there's already a Mamba former thing. Mamba former is though more of a hybrid thing where you alternate attention layers and RNN layers. This is different. This is really making one layer that's both. So it's like, and this is more related to the infinite attention that we talked about a couple of weeks ago, where you sort of have your what is it, query value, key value,
value.
matrix cache in kind of an RNN type thing. So, but this is not exactly that. So this is more like you've got your input and it goes down the this is your context buffer for your transformer, and then when it ordinarily would just fall off the end, it now goes into your RNN, which in this case is two parallel RNNs. It's basically Mamba with a 2x state expansion, and so you just combine them in the usual way, and so the next layer gets to retrieve memory out of this RNN hidden state, and it can also it's also got the results of the transformer. So there's the attention output that combines with that. So that's kind of my grand finale of how far I can push IIR, FIR filtering, transversal filter is another name, and IIR filtering, one pole, two one poles. And so these matrices have, of course, got the query and key and value. And so I came up with some value. And it also suggests a different normalization. So, in the transformer, you have 1 over the square root of the model dimension in the attention head. And then you run all these things into a softmax, which kind of exponentiates it. And the normalization is supposed to make the softmax better behave and so on. But my hypothesis is, well, what if it's just trying to approximate power normalization? Well, now we can just do that, right? So if you just normalize by 1 over the square root of the sum of the query times the key squared, then that's power normalization. That makes the sum of the coefficient squared be 1, and that's the power normalized choice. And so you might not even need an RMS norm after this. You're staying on the hypersphere on average, it's statistical, but we've got power normalization everywhere, then maybe RMS norm is not even necessary. It's just a hypothesis. Anyway, it just looks good from a point of view of somebody who likes normalized signal processing. So then I have a list of things I'd like to do, and then finally my closing slide where we get to meditate on this mandala.